have that completely done by next lecture. So the first 2/3 of the lecture today will be do a deep dive. By that I mean setting up for the first time a differential equation. I call it differential analysis. An equation of motion or momentum applied to a tiny control volume of dx dy. And that resulted in an equation we call the Euler equation. It's still a bit intricate calculus, so I'm going to make sure I don't go too fast and then digest it. And on that basis, there's a homework in class that will announce when I go through that derivation. It's one of the 3 homework due for next Tuesday. And all that effort is to show you where is the origin of the Bernoulli equation. And then with that, I will touch on the 2 new homework. So that's probably the first hour. The remaining 15 minutes, I want to start a new chapter, chapter 7, on how to do an experiment to verify some of your calculation or engineering estimate. That's called dimensional analysis. So the reading will be posted on Travis. It's a special problem, SP1, for special people like you. It's on Bernoulli. So read it, because Tuesday we're going to set up that problem. It really tests your fundamental understanding of the Bernoulli equation. And then remaining session on chapter 3, 5, and 6, and that's it. Bernoulli, you've seen it in 21-24, so we're not going to do a lot of discussion on that, other than to derive the equation for you from first principle. Homework is a little on the heavy side for next Tuesday. 3 problems, 2 from the text, 1 is in class, which you will find out momentarily in about 20 minutes, and another set of homework a week from today. Okay? So that's where we are. Any questions before I start? Oh, the quiz has been graded, and some of you didn't pick up the pie one, so make sure you pick it up in the folder. All right, so let me start with the Euler equation. It's not pronounced as Euler, it's Euler, it's the French name, named after the person who came up with this equation first. And that name specifically refers to where we make an assumption to neglect viscosity. So every time we say I'm using the Euler's equation, inherently I'm telling you I'm neglecting viscosity and hence the implicit flow. And the way we will look at this for the Bernoulli equation is to first look at a coordinates, not x and y, and not cylindrical or spherical, but a streamline coordinate, which I have yet to define for you. What I mean by streamline, you have some notion of that, but I want to be more formal today as to what I meant by streamline. Another name that can be referred to this equation is called equation of motion. Equation of motion for a particle is F equal to ma. Now I'm looking at equation of motion for a fluid. And it's, again, specifically for an inviscid fluid. So we're going to revisit your calculus and use that to set up a differential equation. So first of all, what is a streamline? I make some example of releasing some smoke upstream of either an airplane or automobile and track it and trace and watch that smoke. The smoke basically identifies the flow velocity in the fluid. And we can use that to see the flow pattern around that obstacle, whether it's a submarine or a bicycle, automobile. The smoke allows us to track that. In essence, that is what we call the streamline. So let me define that coordinate. What do I mean by streamline coordinate? So I have a flow pattern identified by what is called a streamline. and this consists of a locus or array of points that if I all join together, I call that the streamwise S direction. And the essence of the streamline is every point, we call that the locus, every point along this so-called streamline, every point, and one is illustrated in here, is tangential tangent to the velocity. So I pick this point here. By picking that point and using the definition of a streamline, immediately I know the flow direction, namely the velocity v. And there's only one component, only one velocity, not x and y, not vx, vy, not u and v, but just capital V. I know because of the shape of the streamline, the velocity must be tangent to this point. And the direction along this streamline is called streamwise, direction normal, perpendicular to it, and it's outward based on the radius of curvature is positive. So this is what I call the streamline coordinate. And it has some unique feature because I now know the direction of the flow based on my intuition of what the streamline looks like. Does that make sense to you? So mathematically, if you want to look at the Cartesian coordinate in reference to a streamline, V capital, and then we would use our traditional XY component like we have done before. What that said by definition of a streamline is that the gradient of that streamline is the velocity v divided by u, of which is tangent to the streamline at the point of interest. So that's kind of a pretty high level definition mathematically of streamline, but mostly I want you to remember is the fact that if you have a flow pattern that you can intuitively sketch on an object like an airfoil, then any point along that so-called streamline has just one velocity, capital V, and it's always tangent to that flow pattern. Does that make sense? Okay? So that's the foundation, or rather the new coordinates that we will take advantage of in the formulation of the Euler's equation. So a little bit of review of calculus. Again, set the stage to where I can derive the equation. Differential analysis. An element of size dx. This is something you have seen in calculus, but it's important for us to review all the elements. If I have a quantity, theta can be anything of interest to us. Example, pressure, or velocity, or energy. Okay, so it's a general quantity coming on the left side, whereas positive x is pointing to the right. How will theta change from your differential calculus when I move the distance of dx? Anyone remember? In the calculus? Theta plus a change in theta, right? And how would you represent that change in theta? Yeah, very good. This partial of theta, partial with respect to x, and then after you move the distance of del x. So by the chain rule, I can represent this small change in theta from this presentation. So this little calculus revisited will be our building block in formulating this so-called differential equation. Have you seen this before? Right? We're going to use this technique to show how we can come up with the equation of motion for a differential element. So next is the list of assumptions. Already we said by Euler we are implicitly referring to a frictionless fluid. We also assume it's steady. For the time being, just to make the algebra more trackable and focus more on the physics, we're going to neglect gravity. That can be added later on, and we will. So I'm making a list assumption from which I can simplify my analysis. And as such, and this is going to be a very fine detail that I will revisit next lecture after you've done the in-class homework. But it's not intuitive. It's not easy to see that. The equation we will derive for the next 10 minutes is actually applicable to both constant density flow, which is all we've been looking at, as well as compressible flow, where the density can be changing. So that's a little bit of detail that I will revisit next time. Okay, so with all that said, we are ready now to dive in. So focusing in the S direction, which is what we call the streamwise direction, I have S, differential element, is called dx, now it's called ds. I'm going to use this differential element and ask myself, if I apply F equal to ma to this differential element, what's the resulting equation? That's the objective. That's what we are trying to do. So in that process, I have to ask myself, what is the force? What is this differential mass? And what's the acceleration, one at a time? And then when we put them all together and do some simplification, the Euler's equation will show in the form when it's completed. In the S direction, this is the equation of motion in the S direction that we are about to show how it comes about. Consists of a pressure gradient. Gradient because it's differentiated with respect to the coordinate S. Consists of density. It consists of a term that at first sight looked a little bit peculiar. Velocity times the velocity also gradient. How do we go from F equal to ma to this final equation, stochastic? Okay, so let me start with the simple term. Start with the mass, or differential mass. What do you think that will be equal to? Let me lay out the dimension. So I have ds in the streamlined direction, dn, the outward normal, perpendicular. And this is a 2D problem. What is the dimension into the board? 2 dimension. What is the dimension into the paper? See it? is unity, is equal to 1, right, per unit depth. You feel comfortable with that? Every time I say a 2D problem, the third dimension is unity into the paper. Any question on that before I continue? So how do you calculate the mass for this tiny differential element? What's the volume of this mass? Density times volume give me mass, right? So I have density, and the volume of this differential element will be dn ds and 1, very good. So that's how I evaluate the mass of this differential element. A volume, which is 3 sides, dn, ds, and 1, times the density. If this is the x, y, z coordinate, then that will be replaced by dx, dy, dz. And we'll do that in a month when we look at a more general Cartesian coordinate of the Euler's equation in 3D. So this is 2D, plus it's limited to a streamwise type coordinate system. And it's advantageous because I can take advantage of the fact velocity is always tangent to my streamline, and that's what we're trying to do. Now the acceleration is a little bit unusual. You may tempt to think that, hey, I was told the velocity, or whether it's a steady problem, so your intuition may say, Dr. Ng, you told me everything's steady, it doesn't change with time, so acceleration should be 0. For a particle problem, that's correct. But it turns out for fluid, and we'll examine this later on when we come to additional differential analysis in about 2 weeks. This acceleration is not steady. Let me illustrate that physically. I have a nozzle, steady problem, no change in time. As the flow goes through this device, is there any acceleration? Yes. Acceleration in space. When I go from point 1 to point 2, the flow has to accelerate. That's called spatial acceleration, which we will look at in more detail later. But right now, just alert that because the fluid characteristic, even though I'm not changing in time, I still can have acceleration. All right, a little bit counterintuitive, but I think when we have more examples to illustrate that later, I hope you will agree with me. So acceleration is not 0. Let me stop. To answer any question for you in this new concept. Yes?
So like this, because you just mentioned spatial acceleration, would that dvds term be considered spatial acceleration?
I'm sorry, which one? DVDS?
Yeah.
It is. That's exactly what I'm going to say next. So this is a very peculiar term, all right? And we will have name for each one of those later on. But right now, I'm trying to, as a first taste of differential analysis, I try to make it as simple as possible. All right? So this is kind of an appetizer of what differential analysis is about. And we will simply do this now for the benefit of deriving the Euler's equation. Then maybe a month later, we'll come back to this and look at this in 3 dimensions. So you will see an Euler's equation in 3D of x, y, z coordinates. And then you will see the viscous equation, again in 3D, x, y, z, called the Navier-Stokes equation. And that's the equation that's the holy grail in fluid mechanics. That means no assumption made. You can throw it in the computer and solve for any problem you want. All right? So this is just a very small baby step. So the way I would look at this chain rule is to recognize the fact that the second term, rate of change of the coordinate s in the streamline direction with respect to time is actually just my velocity, right? change of distance with time. So now I have this somewhat new term, and it's the first time you see it, it's kind of against your grain or intuition. It represents some type of acceleration that is not time dependent, but spatial dependent. Just like the nozzle problem, when I march through the nozzle, even though it's steady, spatially I accelerated, and that's represented by this term. All right, does that make sense to you? It's a little bit new, but they all add up and they're consistent. So now I have a new acceleration that I have to contend with in this problem. Any question before I continue? So the next term for F to the MA is now my forces, and that again is somewhat peculiar. So the forces, my first observation is the fact that this is a differential element internal to my device, and I don't even care what device it is. And contrary to our thinking about a momentum equation applied to fluid, now I don't have so-called an anchoring force. I don't see it because it's all within. Again, it's an also problem where for the control volume analysis, we say I have external force that required to anchor it. But now what I'm seeing here is this tiny guy, internal to my device of dx dy or ds dn. And with that, anchoring force doesn't appear. So the force left is only due to pressure, because I neglect gravity, no body force, and I assume it's frictionless. So now I have to use this differential formulation to ask myself what is the differential pressure acting on my element here. That's my only task left to come up with the final equation for Euler's. All right? So let's walk through that once, and your homework will basically repeat this analysis in the other direction.